Good afternoon. Shortly, we will hear an interesting lecture by Mr. Yossi Cohen on factors and consideration in computer vision IoT system selection. This webinar is a part of webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within Engineers Association as a cluster of photonics entities. Our mission is to deepen the knowledge in photonics and to encourage cooperation both within Israel and with photonics entities in the world. We are holding a weekly webinars on various photonics topics. We invite you to sign up to follow the activities we hold, which are published in our monthly newsletter. Per your request, the newsletter will deliver to your mail. My name is Shlomo Glaser. I am the manager of Photonics Israel. Mr. Cohen is a video and computer vision engineer for the last 30 years. He held B.SC and MBA from the Technion. In the past, he held the R&D and management positions in Intel and in Qualcomm. Nowadays, Mr. Cohen is the CTO of DSP-IP, a video and computer vision software consulting company. Their expertise are applied in the fields of autonomous systems, drones, Agritec, and video analytics. Mr. Cohen, the floor is yours.
Okay. What is the audience designed for this lecture? I'm doing this lecture for startups and MVP developers developing the first version of an IoT product. When developing the first version of an IoT product, it's very important to pay attention to the development time and cost, and less to cost reductions and delay cost reduction for later phases. Sometimes companies start with cost reduction. They want to design a product which would cost unknown amount of dollars, and also would do everything possible that they dream about. And it can be done usually. What this lecture is about is advising on what are the best solutions for starting such an MVP product for computer vision. And we'll compare the options that exist in the market, the most common options. We will see what is CPU, GPU, and TPU, and how they are processing deep neural networks. And later we will review development boards and the accelerators and compare them, so we will know what to choose for our solution. So this is what we'll do in the lecture. What are the IoT functions? In the past, IoTs mostly worked as controllers. They control motors, open gates, took pictures, and did basic image operations, usually OpenCV, using OpenCV. If the processing took too much power, then those IoT devices would send the images to a cloud or to a local computer for further processing, for storage, and for decision making. For example, open a gate based on a detected recognized face. So this is what we have done in the past, only 3, 4, 5 years ago. What are the roles of modern IoT devices, which include computer vision? That include reading numbers, license plates, road signs, detecting faces or cats and dogs, usually in examples, counting people that we detected, segmenting car, pedestrians and roads, scanning the environment and navigating, also doing SLAM, and integrating all of this to driving cars or flying drones. What is the basic idea of neural networks, since all of this is done with neural networks? The basic idea is to multiply inputs by weights, and inputs is usually pixels or pixel colors. Neural networks exist for over 60 years. They begin The weights were even computed analogically by resistors in the 50s. And deep neural networks, which are done today, usually include 100 or more layers. For example, ResNet 103 include 103 layers. That means hundreds of millions of weights and heavy matrix operations. So how does the different processing architecture compute those heavy matrix operations? And what are the operations, what are the types of operations we are using deep neural networks for? The network we are using are LSTM RNN. Those networks are used for series processing, for example, for sound detectors like gunshot detector, for data series processing to predict the number of clients in a restaurant. Activity detectors detect the activities the user is doing based on accelerometers or even based on images. Those networks require very low processing powers compared to CNNs, which we will review now, and could be done even on Arduino or Raspberry Pi processors. For this, we don't need any TPUs or even GPUs. So CNN, convolutional neural networks, CNN has several types of functions which we'll review right now. The first one is classifier. Does the image include the type of object I would like to search for? For example, a cat or a face. This is the basic classifier. A common implementation of the classifier, or even the first implementation of the classifier, was the LANET network. Box detectors. Box detector detect where is the object located and draws a box around it. It used to detect people, faces, corona mask, that's very common recently, cars, road signs, and of course cats. Known box detector, or the most common box detector, is a YOLO 3. The most recent one in the series is YOLO 5, which is actually not the same architecture or by the same group which created the YOLO 3, but it's still a YOLO 5. And another one is a single shot detector, the SSD. Another type of network is the segmentor. Segmentor doesn't find the cat, it defines for each pixel if it belongs to a cat. So it doesn't even know if there is one cat or two cats if they are next to each other. A basic implementation of a segmentor, or the most basic one, is FCN8. And as I said, it does not separate between different objects. To separate between adjacent different objects, we need a multi-instance segmentor, such as the MRCNN network, and it decide if a pixel not just belongs to a cat, but to which cat this pixel belongs to. Of course, this network is much heavier than other networks like the YOLO or the classifier, LANET. How does the processors, the different type of processor, process or operates on a deep learning task? The first processor we will see is a CPU. Example of CPUs are Intel processors, ARM processor. They are processing instructions sequentially, and as such are very unsuitable for matrix operations. To enhance the capability of those processors, some enhancements were done, like single instruction multiple data units, like the Pentium MMX and later SSE and SSE2. And after this path was exhausted, multi-core insertion of multi-core in a single SOC 2, 4, and 8 cores. But as we can see from this graph right here, the increase in performance of the core is not linearly related to the number of transistors, meaning that we are exhausting our options to increase the performance of CPUs. So CPUs are not very good for matrix operation or deep learning operations. Another graph that shows us this, actually it is called the end of Moore's law. For sequential operations, maybe. For sequential operations in silicon, I think that could be a good definition for this graph. Of course, there are other options to follow Moore's law. We'll see that in other lectures in quantum computing or other methods. GPU. GPU today is much more than a graphical processors. GPUs are using hundreds to thousands, and in the Lovelace processors, even almost 20,000 cores. It's much better in parallel processing than CPU, since it has hundreds or thousands of cores, and it is much better in processing large matrix operations. I think the most common GPUs are by Nvidia, Nvidia 2080 card, or the Nvidia T4 for servers. But GPU is not an IoT solution by itself. We can't place a T4 card and let it process, for example, a single camera. It requires a computer, and that would be expensive. So it's not an IoT solution by itself, but it could be included as part of an IoT solution, as part of a SOC that is doing IoT operations. TPUs. Unlike GPUs, TPUs are very recent, from the last 4 years. They are built only for deep learning, only for large matrix operations, meaning multiply and accumulate, as we have seen before here. So, for example, think of a network with 1,000 or more nodes that require processing. A TPU could do the entire layer, something that could take a CPU a lot of time to do in a single operation. Example of TPUs, the first one was Google Coral, and later companies like Huawei, Nvidia, and Intel created their own TPUs. In every phone in the last years, meaning high-end smartphone, there is a TPU today. In Samsung phones, Apple phones, and Qualcomm-based processor phones. In Israel, companies like Habana and Halo creates TPUs, Habana for the server side and Halo for the IoT devices. This is the architecture of a TPU. As we see, the main unit, and let's say that most of the silicon in the processor is dedicated to the matrix multiplication unit that could do thousands of multiply operations in a single instruction. Think of it as a very, very large SIMD unit. So if we will compare the different processors types, CPU, GPU, and TPU in performance per watt, we will see that TPU is 83 times better than a CPU. Actually, in some comparison, it's just 14 times better than a CPU. So obviously, we should choose a TPU for IoT device, actually that's not the solution because the TPU can't work by itself. It requires a CPU to do the general processing, and in some cases a GPU for the display or other processing. So a solution would not be a CPU, a GPU, or a TPU, but a SoC which includes both CPU and GPU, and sometimes a TPU on the high-end models. What are the dev boards and accelerators we have today on the market? First of all, if we are a company which already has a device in the market, for example, I'm a company that has a Raspberry Pi device, and I wouldn't like to port the entire code and operation and packaging to a new device, I could test an accelerator. Some accelerators connect to the board by USB. They also have a small SoC form factor that could be integrated into a PCB. But for testing and development, it has a USB connection. The development options that we have are the Coral by Google. It's the first TPU accelerator in the market. The Intel Movidius, company that Intel bought a few years ago, and the Rockchip RK1808. All of them could connect, for example, to a Raspberry Pi 3. This is the most common usage, and accelerate its performance. But if I was developing a new product, I wouldn't choose an accelerator. I would choose a solution which already has a TPU inside. Also, the accelerators in this form factor cost around $100 per unit, and in that, and for that I could buy a Jetson Nano, for example, which is actually the same processing without the cost of a Raspberry Pi and the connection and everything. So what are the SoCs we have today and how they are looking? Usually a SoC would have 4 to 8 ARM cores, a GPU, either an ARM Mali, an Nvidia, whatever, or some kind of an Intel Iris GPU. And sometimes it also includes a TPU. So the selection, as we said, is not CPU, GPU, or TPU, but selection between SoCs. Or even not a selection between SoCs, but a selection between development board, which include different system on a chip. So that for an MVP or for a company that has a short time to market for development, we will choose the development board and work on that development board. We will not go to a PCB editing session. What are the factors we should consider? First of all, the price, but sometimes on MVP we will consider it less. It's less important than other factors like the development time. The unit performance, it must have the performance to do it fast and not to send it to the cloud if it's not necessary or designed. What is the power if it's a mobile unit like a small car or a drone? The longevity, what is the life cycle of the SoC, for how many years it would be supported? What is the code base? For very short development time, it's very important to have a strong, good code base, existing open sources and solutions, development communities, and also SDKs by the vendors. Both Intel and Nvidia have strong SDKs. And what is the connectivity of the board? Some boards are lacking in connectivity, Raspberry Pi, PCIe, Jetson Nano does not have Wi-Fi, and so on. So it's important to check the board connectivity. Okay. Pricing, starting from $10 or less for Arduino, $35 to $75 for Raspberry Pi 3 and 4, depending on the amount of memory. $59 to $100 for Jetson Nano, depending if it's 2 giga or 4 giga. Intel Movidius accelerator, that blue USB stick, cost $100, which is the same as Jetson Nano. And since it has the same capacity, it's better to use the Jetson Nano because Jetson Nano stands for itself, while the Movidius requires some board to be that will connect it to, so it costs more. Google Coral board or accelerator stick is $115. Rockchip development board is $175 to $300, depending on the option. Jetson TX 200, and Jetson NX 400, and Jetson Xavier 700. So what do we get for all this money? I found this comparison only between the Nvidia products. We see that the Jetson Nano could do for most of the image processing tasks something like 10 to 15 FPS, while the NX that cost 4 times more could do about 4 or 5 times higher performance for those tasks. And the Xavier, which costs 7 times more, which could do something like 20 to 30 times the FPS of the Jetson Nano. Okay. Operating systems, we usually prefer Ubuntu on those boards, and most of those boards would run Ubuntu. Some of the boards could also run Android, and Raspberry Pi usually runs Raspbian or Raspberry Pi OS. And for some boards, we could install Ubuntu or even Windows, but it's not an easy task. So if you want Ubuntu, Raspberry Pi is not the greatest solution. Longevity. Example of longevity, sometimes manufacturers are having troubles with the lifetime of their processors, in some cases on the lifetime of the camera or ISP unit. So it's important when designing a product, not an MVP, but a full product, to look at the longevity of the unit. For example, if we look at the Jetson TX1, which is an old processor, it ends right now, tomorrow. So even if we'll see that the Jetson TX is a great price, Jetson TX1, we wouldn't use it if we couldn't buy it since the manufacturer stopped manufacturing it. So longevity is an important factor, less for MVPs, but mostly for products, for fully developed products. We'll start with the boards now, starting from the lowest cost boards to the highest cost boards. Raspberry Pi 3 and 4, as we said, it's $35 to $75 depending on the amount of memory. It's the most common development board in the market, which is used in the market as a product, inside of products. It is mostly a controller with a good connection to cameras. And for processing, it could do something like 3 to 5 FPS of tiny YOLO, which is nice. It could be used for some image processing tasks, but not for everything. For heavier tasks, we should take boards which cost more and has more performance. Let's call it the second most common boards in the market, and a board that I see a very high adaptation of is the Nvidia Jetson Nano. If we compare it to Raspberry Pi, it could do something like 10 times more of tiny YOLO. And it could do a lot of other open computer vision tasks, which the Raspberry Pi can't, as we can see by this comparison by Nvidia. It has a relatively strong GPU in comparison to the Raspberry Pi, and as I said, it could do 25 FPS, meaning real-time video of tiny YOLO. Rockchip. Rockchip is a very strong manufacturer, less known by companies. It doesn't have high visibility as Nvidia or Intel or Raspberry Pi, yet it has a very strong chip and not very strong SDK or support. The boards cost $175 to $300. It has all sorts of connectivity, including PCIe, USB 2 and 3, GPIOs, and of course, a very strong TPU. When using it, consider the amount of support you are getting. On the other end, there's very good pricing for the chip itself, and it also is gaining adaptation in the market recently. Intel has a series of Atom boards called up boards. Pricing ranges between $200 to $700, whereas higher costing boards also include RealSense 3D cameras. For development, Intel uses the Openvino Sdk, which assists in the development and optimization of the neural networks. One of the advantages of using Openvino is to code once and let it run on all the boards and devices or processors by Intel with the same code base, meaning that I could take the network I built for a server and run it on an IoT device and port it to an IoT device using the Openvino Sdk. It's not very popular in the market currently. Although the Openvino is a strong SDK also for server-side processing. What we see that is adopted in the market is a RealSense camera by Intel, although the boards are usually by Nvidia. So Intel is strong with the 2D, 3D camera, with the 3D cameras, but not so strong with the development boards for IoT. Jetson NX, a $400 device. It's a mid-range IoT device by Nvidia. Mid-range is it's pretty recent, something like 6 months. Just out this year. Mid-range because it's between the Jetson Nano and the Jetson Xavier, which costs $700. It is about 4 to 5 times stronger than the Nano. It has the same Raspberry Pi-like form factor and connectivity, a little bit bigger. It has the MCC and PCI connectivity, and what we can do with it, for example, is something like 16 to 20 video streams processing in parallel, as we can see in this image. So it's pretty strong, and it could save us from sending all those images to the cloud and only sending the metadata of the detections. This is part of the deep stream video analytics architecture by Nvidia, which is a very strong SDK for video analytics. The software and open source solutions that we have, Raspberry Pi does not have an SDK by the vendor, but it has a very strong open source community and open source solutions, so we could take and integrate a lot of things. but it doesn't have an SDK like the DeepStream or Openvino. The DeepStream and Isaac are two very strong SDKs, one for video analytics and one for robotics. The Isaac is actually built over the DeepStream, and it accelerates, it highly accelerates the development of video analytics solutions. Things that could take a year or two in the past, we could do it in a day or two today using the DeepStream. We could deploy something like hundreds of camera video analytics solution using the DeepStream without any effort. Something like that in the past could take a lot of time to develop and integrate. Openvino is also very strong. It is the main advantage of it is code once and deploy on any processor, since Intel has a wide range of processors for both server side and IoT. So this is its strength. For video analytics, it's not designed for video analytics per se. It's more for development and optimization of the network. It could include features like Nvidia's TRT SDK for optimization. The only device that I would look at this lecture besides the board itself is the camera, because the camera costs a lot of money, so it's a factor when selecting a solution, and also because the camera highly affects the results of our product. It's important to have a good camera when we are developing the product. Sometimes we try to save money on the camera, and then it takes a lot of time in development to compensate for that, since the camera is not very good, the ISP is not very good. So it's important to look at the camera and the factors that affects its selection. What are the camera features that we should look at? First of all, connectivity. If it's connected by MIPI, USB, or in some high-end cameras by HDMI, the resolution, the format, YUV, JPEG, and in some cases Bayer. If it has HDR support, what is the dynamic range, what is the pixel size on the sensor, what filters to use, if to use an IR cut, what is the lens quality, the field of vision, the lens distortion. It's important in computer vision applications when we measure distances and objects, the distortion could hurt our performance. Isp quality is very important for deep learning, since Isp compensates for light, for flicker, for color ranges. So Isp quality, to have a good Isp on the camera. Not all cameras are supported by all boards. For example, Raspberry Pi 1 camera is not supported by Jetson Nano. So it's important to check that the camera is supported by the board. If it's a USB camera, then USB cameras has UVC support, meaning that they don't need development of the drivers on Linux and Windows, and in our case, on Linux boards. So it's important. In most cases, I would prefer a USB camera due to the UVC. UVC is a universal video class, a feature which makes developing a driver redundant, since it's automatically supported by the Linux OS, also by the Windows. If we are developing a 3D camera, then there is a lot of processing to do on the processors. And the manufacturers saw that and saw an opportunity to incorporate a processor or a vision processor AI processor inside the camera. So if we use a regular 2D solution, 2D camera solution and 2 cameras and perform all the processing for the depth map on our own on the processor, it would take a lot of processing. So the manufacturers of the cameras or the manufacturer of the AI deep learning chip, so this is an opportunity to integrate their processors inside the camera. So the most common line of 3D cameras is the Intel WillSense family. Another option is the Rockchip RMSL, and an Israeli option is the Veronica by NUT. What is the RealSense? RealSense is the line of camera. D455 is the recent, D435 and D415 are other cameras in the line. They have an IR camera, an RGB sensor, an IR projector, and dual cameras, which provide us with an option for a 3D camera. In some cameras, there is also an IMU unit, which is integrated into the camera for robots or drones. It has a built-in processor inside the camera, so it doesn't output only the video from the camera, but also the depth map. And that's very important because it saves us a lot of processing. Those cameras does not fit Raspberry Pi 3 in high resolution due to the high data rate that the camera creates. Another option is the NUT Veronica. It's designed for robot, drones, and AR. It has low latency to avoid AR motion if we are using it over an AR unit, an AR helmet, or AR glasses. It has an on-chip SLAM, a built-in visual processing unit, and it outputs a depth map, same as the RealSense. Another option is a Rockchip RMSL. It also has a depth camera and built-in VPU and DSP, and output a depth map, like the other cameras. It has a projector and IR sensor and RGB sensor. So if we summarize everything, there isn't a winning solution. The solution that you will have to choose depends on the product that you are developing, on the cost, on the development time. I highly suggest using a development board and not going to a PCB on the first phase of the MVP. Robotics drone solutions usually highly differ from video analytics solutions, since those solutions should pay attention to the form factor and the power, and not only for the cost. We should, in the MVP or first phase, pay attention to the development time and cost, and the development time and development cost over the price performance cost of the model itself, of the product itself, since cost reduction should be delayed to later phases. We should also select a product with good, well-tried SDKs and communities, for example, the Nvidia DeepStream and the Intel Openvino. And I think that's all.
Okay. Yossi, thank you very much for this interesting lecture. It's time for your question. I'm talking about the audience. Please don't hesitate. It's your time. Would you please provide us some examples verbally of application in different area, like in drones or in autonomous systems? So we will understand where you implement this type of solutions.
Okay, for example, smart camera, smart video analytics cameras that check if people are at very close proximity to avoid corona distancing, to check if people has face mask. This is a very nice exercise for students and something we implemented ourselves. To check the lines next to counters in checkout to see if there is something needed to be done to increase the number of cashiers. So this is an example of video analytics. A nice example of video analytics is people counting, to know the number of people in a mall, for example. Another example would be that's in video analytics. In drones is, for example, a self-flying drone, which could also take images of Agritec and decide if it requires irrigation or to see the level of maturity of the fruits, or to check for bugs in the crop, to check the land. Another example is in the building industry. There are many drones and robots in the building industry, robots that does the painting of the walls, for example. It's a real company. Robots, drones that check the building site and compare it to the plans. There are several companies like that in Israel. So that's in drones. In small, very small cars, there are example of cars, the self-driving cars for food delivery, Nano and other companies. Actually, it has devices. It's something to there is a board called Nvidia Drive, and for that board, it has two Nvidia AGX Xavier processors. Something like it cost a few $1,000s. But it could drive cars, and it has all the SDKs required for driving a car, and it is built over existing SDKs that we saw. So on the lowest layer, there is a Deepstream SDK. Above it, the Robotics SDK, which is used actually for very small cars, like this one. Okay, so the Isaac SDK could be used for this type of cars or even a little bit bigger. And above it, there is the Drive SDK, which is used for fully matured or full-size cars. Okay. So those are examples. Anything? Any other questions?
Yes, you have a question from Danny Al-Bukhair. You can read it on the Q&A, I believe.
Okay, where is... just a second, I'll stop sharing. Oh, there is the Q&A. Level example of how many different objects one of those can handle. What affects this? The GPU, the memory. Actually, what affects it is the network. For example, a YOLO could detect 50 objects or 100 objects, although there are specialized networks for many face detectors. For example, for detecting 1,000 faces in an image, that's an article I saw recently, there was a special network. But example of a YOLO network could detect 50 faces or 50 animals in one or 100 objects in a single image. So there's no problem, it does not relate to the memory of the unit or the GPU of the unit. what would the unit performance affect is the number of times I could call this detector. So, for example, in a small unit, like a Raspberry Pi could hardly do a tiny YOLO on a very small size network, on a very small size image. If we take Jetson Nano, it could do 25 FPS of tiny YOLO on a 400 by 400 image. And if we took a Jetson NX or a Jetson Xavier, it could run a YOLO, not even tiny YOLO, in real time on much larger resolution, and so detect much more objects. So what affects the number of objects is the network size, and for what the device type determines how many times we could call those networks in 1 second. That's the FPS that I showed previously. What about the Intel Movidius-based solution? I showed the Intel Movidius-based solution in the, just a second, I showed it right, the blue stick, right, just a second, where is it, here. Just 1 second, I'll share the screen again. Here. So I discussed the Intel Movidius processor as an edge processor and accelerator right here as part of the edge TPU accelerators, and said that we could use it with existing solutions. So if we are not an MVP developer, but a company with a Raspberry Pi free board in the market, and we would like to increase the capacity of this board to allow for processing of deep learning tasks, then it's a good solution. Okay, next question. Q&A. Okay. Any difference in model updates, remote management simplicity between the SOC you have presented? Actually, this part is in the slides I skipped, and it's not related to the SOC or the dev board itself, but to the cloud processing. I'll share the screen again. I just didn't want to go beyond my time, my allocated time, but if we'll go here to cloud connectivity, do you see the slides?
Yes, we see the slide.
Okay. Both AWS and Azure as cloud IoT solutions, and as such, they manage the different boards and enable automatic software updates of the boards without writing any software by us. So if, for example, we have something like 100 or 1,000 Raspberry Pi or Jetson Nano or Jetson NX somewhere in the field, and it has internet connectivity, we could update them with a single push of a button using the AWS or Azure infrastructure or cloud IoT solution without writing any codes, and that's really great. So I showed here a solution by AWS called AWS Greengrass for IoT management. And in this case, it's for Nvidia solutions, but in the past, I used it myself for Raspberry Pi solution, Raspberry Pi boards, and it worked great. And the architecture itself sends the metadata gathered by the detectors running on the board itself to the cloud for further processing and storage and analytics. And as part of the architecture, it also handles the security, the synchronization, and the software updates. So this is a nice, nice question. Sorry for skipping it. I just okay. So this is the updates, and as I said, we could do the update from the IoT cloud. Then in terms of wattage, are any of the IoT solutions efficient enough to work on USB power? Of course, Danny, as I showed, all the solutions here are using USB. All the accelerators I shown here are using USB power. See? Both the Movidius, the Rockchip, and the Coral could work on USB power. This unit is a USB. You can see here is a USB. Rockchip is a USB, and Movidius is over USB. Shai, another question about the Movidius. Just a second, it's loading. Well, I'll have to look and answer it afterwards, but the Movidius, for example, is used as a VPU inside the cameras. We could use it inside the RealSense camera. There is a VPU there by Intel, and for their IoT, devices, they are using Atom boards, which does not include the Movidius. So the app board does not include the Movidius. Any other questions?
Well, I think that it was a very interesting lecture. Thank you very much.
You're welcome.
And I would like just to the audience to know that we consider to have a course that will run by Yossi, and we will ask you whether we would like to participate in this course. It will be much more meetings, and we will go deeply into this territory. So thank you very much, and have a good night.
Thank you.
Thank you.
Bye.